Welcome back to the ChemDoctor, and what I'm going to do in this video and the next two or three that come after it is add to the playlist that deals with theoretical yield, the calculation of theoretical yield for a chemical reaction, the calculation of percent yield, and limiting reactant. Now, what we're going to do first is a very simple theoretical yield problem where we're given the moles of a reactant, we're told the other reactant is in excess, and we're going to calculate the theoretical yield of a designated product. Now, what I highly recommend in this video and the next few that are on this topic is that you have out a periodic table, you have out paper, and a calculator, and don't hesitate to stop the video and run your own calculations. I highly suggest that you work through this with me rather than watching the video passively. Now, when we talk about a theoretical yield, what we mean is we're assuming that this chemical reaction goes to 100%. So let me lay the framework for this. We're going to start this reaction with 0.1 moles of hydrogen gas, okay, and we're going to assume that we have an excess of NO. Now, what does this mean exactly? So if you imagine that you are building cars for a living, the 0.1 mole might represent a completed car body, and when we say that the NO gas is in excess, then what we mean is that we've got at least 4 tires to put on the car body, all right, which would be actually an equal molar amount of tires to car. So to say that we're in excess, then what we would really mean by that is that we would have 5 tires. So we would have 1 tire more in excess than the amount we need to make the car. So what we're saying in this problem is that we've got 0.1 moles of H2, and we're providing enough NO gas to complete the reaction. Now, if we're calculating a theoretical yield, we need to know which of these products we're going to focus on, and we're going to calculate the mass, or we're going to calculate the mass of H2O produced in this reaction. And in a theoretical yield problem, the reason it's called theoretical is we're going to assume that this reaction goes to 100%. So what that means is that every bit of the hydrogen that we put into this reaction is going to react. And at the end of the reaction, there will be no H2 gas left, and we will have produced the maximum amount of water that can be produced in this reaction after having reacted all the hydrogen. Now, we're assuming that the reaction goes to 100%. Let me just put theoretical yield up here. So we're assuming reaction goes to 100%. And in reality, no reaction ever goes to 100%. And the reason for this is you can break it down into 2 reasons. The first is that there are energetics involved in this reaction, which I'm not going to go into in this video, but there are energetics that control how far a reaction will shift to the right and produce products when you have combined the appropriate amount of reactants. And then the second thing is that if you carry this reaction out in the laboratory, there are always losses. Nothing is 100% efficient. But we calculate a theoretical yield because it gives us the absolute upper boundary or maximum that you would expect from this reaction, and then whatever we end up producing will be some percentage below this maximum value. And that's the issue of percent yield, which we're also going to calculate in this problem. All right, so how do we carry out the calculation to figure out how much water we're going to produce? One last thing to remember: every balanced equation has coefficients. These would be these numbers that I'm underlining in red. The coefficients are in units of moles, and what they tell us is the ratio in which the reactants react and the ratio in which the products are produced. And you can think of these coefficients much like the tire example that I gave you. So we know ratio-wise that to make a car, you need 4 tires for every 1 car. All right, or if we're going to bake bread, you're going to need a certain number of cups of flour in proportion to the amount of water that you add. So the coefficients tell us the ratio in which things react and the ratio in which things are produced. So in this reaction, we need 2 moles of NO for every 5 moles of H2 to produce 2 moles of NH3 and 2 moles of water. So in any theoretical yield calculation, you're going to need to use the coefficients. So to calculate the amount of water we're going to make, what I'm going to do is take the moles of H2 gas and I'm going to pull them down over here and rewrite them. So it'll be 0.1 moles of H2. And now we're going to use unit multiplier, and what I'm going to do, since we're already, note something here, since we're already in units of our coefficients, all right, we don't have to do any initial calculation to change the hydrogen gas into a different unit. We can go directly towards calculating the moles of H2O produced. And to do that, we need the ratio from the balanced equation. So we're going to solve for the water, and using unit multiplier method, we're going to put what we want to solve for in the top of the fraction. And in the bottom of the fraction, we're going to put what we want to cancel out. So we're solving for the water. It should be in the top. We're going to be canceling the H2. It should be in the bottom. And then we're going to multiply 0.1 times 2/5. All right, and what you should get will be about 0.04 moles of H2O produced. All right, now to get to the mass, we're literally just one step away. All we need to do is calculate the molar mass of water, which is 18 grams per mole. All right, and so if you look at your periodic table, the hydrogens are each worth about 1 gram per mole. There are 2 of them, and that will be added to the molar mass of the oxygen, which is 16, for a total of 18 grams per mole. And I'm rounding here because the main aim of this video is to teach you how to calculate theoretical yield, and I'm not going to be concerned about significant figures. So now at this point we've got 0.04 moles of H2O. To get to the mass, all we need to do is multiply by the molar mass of the H2O, which is 18 grams per mole. And you can see clearly, and I'm going to emphasize this, you really need to understand the units. You can see clearly that the moles are canceling out. And we have successfully calculated the grams of the H2O, which you should be getting a value that's about 0.72 grams of the H2O produced. Now, this is the theoretical yield, and it is the maximum amount of H2O expected in this reaction if all 0.1 moles of H2O reacted and the energetics allow this reaction to literally go to completion, to go to 100%. All right, this is our max H2O that we can produce. Now let's say that we actually ran this reaction in the laboratory, all right, and at the end of the reaction we took the water that we produced in a reaction flask, set it on a scale and massed it, and say that when we looked at the scale that we discovered that the actual yield, the yield that we actually got in the laboratory, was 0.21 grams of H2O. All right, 0.21 grams is the actual yield. Then what we're going to do next is calculate the percent yield. All right, and percent yield will give us the essentially it's a way of looking at how efficient this reaction was, and it's equal to the actual yield divided by the theoretical yield, which I'm going to go ahead and abbreviate, times 100. So for this reaction, percent yield would be 0.21 grams. Whoops. My dyslexia coming out. 0.21 grams divided by 0.72 grams, all right, times 100. Okay, and the percent yield for this reaction, therefore, you should get around 29%. Now, whether or not this number actually means anything, you have to know more about this reaction. And what I mean by that is that you need to know about the energetics, number one. And like I said, I'm not going to get into that in this video, because the energetics may control this. You might not be able to do better than this. But the other side of the coin is the person doing the reaction and how many losses occurred over the process of carrying out the necessary steps to actually do this in the laboratory. And laboratory or experimental work always involves losses. So we would need more information before we could actually look at this number and judge whether it's a decent percent yield or whether or not it's a matter of incompetence in the laboratory or what. So at this juncture, what's important is to know how to calculate it. To know what the number means is something that you would need more information for. All right, and with that, I'm going to go ahead and close this video.